Welcome to the lecture on concept of similarity in physical modeling. So, in the last lecture we talked about the physical modeling principles. So, as we discussed that there the similarity principle or its concept is important to be kept in mind when we are making the physical models, which is normally a reduced scale model. And because the model in most of the cases the system involves the flow of species, flow of the fluid, you have chemical reactions taking place, heat transfer taking place. So, how to predict properly, you need to have the similarity principle similarity satisfied. So, you have as we have seen that for the faithful representation of flow in the model tundish, there should be constant ratios between corresponding quantities in the model in the actual tundish. So, you will have the quantities like you have the velocity or the geometric dimensions or the velocity or the heat transfer values, suppose, which is there in the actual tundish and in the model tundish, all needs to have a ratio. So, that is that should be maintained for the model and the actual tundish. So, for melt flow in the tundishes, the states of similarity which we normally include is the geometric similarity, kinematic similarity, dynamic similarity and thermal similarity. So, many a times we call it as a geometric similarity or even mechanical similarity, thermal similarity. Apart from that, also we have the chemical similarity that may also be there wherever the chemical reaction is taking place. So, but in normal case when we talk about the similarities, we normally talk about geometric, kinematic, dynamic and the thermal similarities. So, we will talk about these similarities. Now, the geometric similarity is it tells that the actual tundish and its model must be geometrically similar. So, when we are making the model tundish in which the flow has to be there, so they should be geometrically similar, means that the ratio of their geometrical parameters they should remain constant. Like if you have a tundish of 3 meter length, and if you are making the model tundish of 1 meter length, it means the ratio of the two will be 3. If you take the ratio of the prototype to the model, or if you take the ratio of the model to prototype, it will be less than 1, that is 1 by 3. Now, this 1 by 3 is basically, so it is a 1:3 model. So, we can say like that. So, 1 by 3 will be that scale factor, length scale factor. So, this has to be maintained in all the geometric dimensions, like your width also should be accordingly you have to adjust, which should have a ratio of 1:3, similarly for the height also. So, it is telling that so this is how all the length dimension of the model tundish should bear a constant relationship with the corresponding length dimension in the actual tundish. So, that is how we try to represent it, like Lm will be Lp into lambda. So, m refers to the model and p refers to the prototype. So, lambda will be Lm upon Lp. So, lambda is known as the scale factor, length scale factor, and it is if you are taking a reduced scale model, in that case it will be less than 1. If you are going for the scale up model, it will be more than 1. So, so that way in most of the cases in tundish flow or so in the steel making, we normally make the reduced scale model. So, the value of lambda will be less than 1. So, if you try to see that, you will have, suppose in the case of your actual tundish may be like this. So, you will have in this case you have the molten steel here, and you will have the level of steel suppose here, and then inlet is from this side. So, your molten steel is flowing. So, you will have inlet stream from ladle. Now, this is your normal at the normal scale you can have a physical scale. So, you will make suppose about 60% or so. So, it will go like this. So, this way you can have a physical model here. So, you can have this dimension to this. So, this ratio to this ratio dimension, or this ratio to this ratio dimension, like that. So, that should be a constant value, that is your so this length by this length, or its width or so. So, these values have to be similar. So, you will have, this is your model tundish, this is your actual tundish, that is your prototype tundish. So, you will have molten steel, and here you will have water, but the ratio has to be same. So, that is what is the meaning of the geometric similarity. So, similarity is on the dimensions, like you have the diameter in case of suppose your outlet is in cylindrical in the circular type cross section. So, there the diameter will come into picture. Now, the next type of similarity, next is the kinematic similarity. Now, kinematic similarity will be indicating that each corresponding fluid element in the two system should follow a geometrically similar path, and the time interval between the corresponding events should be at a constant ratio, that is your scale factor. So, that is your kinematic similarity. So, then so here they should have the similar time interval, velocity and all that, they will be taking into account in these cases, and they should have the same value if you talk about the x component velocity ratio, or y component velocity ratio, or z component velocity ratio. So, there you will have a constant ratio. So, that we will be talking about the kinematic similarity. Then comes the dynamic similarity. Now, dynamic similarity will be talking about the forces acting in the two system. So, it will in kinematic similarity we are not talking about the forces. However, in the dynamic similarity we will be talking about the forces. So, it will be dealing with the forces which act in the two system, which accelerate or retard the moving element in the system. So, as we talk about any system, you will have different kind of forces which will be acting inside the system, and forces acting at a corresponding time at a corresponding location in a model tundish should bear a fixed ratio with the forces in an actual tundish. So, this will be the dynamics similarity. So, if you talk about the different type of forces, if you go to the dynamic similarity. So, when we talk about the flow in the steel making, so you will have different, normally you have some special some common type of forces. So, suppose you have the inertia force. So, inertia force will be normally denoted by Fi, and it will be rho into V square into L square. So, that is your inertia force, and similarly if you talk about the viscous force. So, normally you have the three kind of forces which are commonly seen: inertia force, viscous force and gravitational force. So, viscous force will be F eta. So, we call it as the eta into V into L. So, that is your viscous force. Similarly, you have gravitational force. So, gravitational force is the Fg, and it is defined as the rho g into L cube. So, these are the different forces which are commonly they are coming to the analysis in the case of the flow in the steel making applications like in tundish or so. So, what we this dynamic similarity condition says that F I of the model ratio of this F I and ratio of the F I of the prototype. So, they should be same as the F eta, that is viscous force for the model to viscous force of the prototype, or the gravitational force of the model to gravitational force of the prototype, and there should be some constant that should be lambda f. So, that is for force. So, the similarity condition tells of the for the dynamic similarity, it tells that these values should be same. So, if you talk about the this condition F I m and that of F I p, and that should be equal to F eta m to F eta p. So, if you try to go further into it, so what you did see is F I m is rho, and then you have v square L square, and that is for the model. So, if the F eta m will be rho V L, so it will be that is eta V L. So, this is eta V L. So, if you take this for the model, it will be same as rho V square L square upon eta V L of the prototype. So, from here what you see, if you further go to from this point. So, what you see, you can cut these terms. So, it will be rho. So, this will be coming to a term you must have come across this term, that is your Reynolds number term. So, it will be Reynolds number of the model. This should be, so here, so we need not go there. So, it will be Reynolds number of the model should be same as the Reynolds number of the prototype. So, this is the ratio of basically the two kind of forces. So, that tells you the value of the Reynolds number for the model, it should be same as the that of the prototype. So, that talks about these conditions which is governed by this dynamic similarity, and the Reynolds number which is found in the model, physical model, it should be same as that which is there inside the actual prototype model. Similarly, if you talk about the ratio of the inertial to gravitational force. So, if you go to this model of inertial F I, inertial force for the model, to inertial force for the prototype, and if you take the ratio for the F G I m to F G p. So, they will lead to another kind of the non-dimensional number. So, what you see here is you get V square by G L of m should be equal to V square by G L, it should be for the p. So, you get the another number, that is your Froude number, and so you get the Froude number for the model should be equal to Froude number for the prototype. So, these conditions emerge out when we talk about these similarity conditions, as especially maintaining the dynamic similarity in the case of fluid flow. So, so if you so what we see that these conditions need to be checked when we are further predicting the values, and then we say that it is dynamically similar, the model as well as the prototype is dynamically similar. Then comes the thermal similarity. Now, thermal similarity is something where we deal with the heat losses. So, when we talk about the water modeling, so normally in water modeling when we do for the tundish, so with that the heat loss which is taking place at that high temperature. So, it is very difficult to correlate, but then we can have these thermal similarity, and what we can do is here also whatever the temperature difference is there, suppose if they are in the same ratio, then we can say that the systems are thermally similar. So, the similarity dictates that corresponding temperature differences should bear the same ratio of the model and the actual tundish. So, suppose at some point you have the temperature in the model tundish, and at the same point you have temperature in the in the actual tundish. So, if the ratio if you are taking at different points, they should be similar. So, that is what the thermal similarity means. Thermal similarity also requires that the rates of heat transfer by conduction, convection and radiation at a given location at a given time in the model should have a constant ratio with the corresponding rate of heat loss in actual tundish. So, similar to the temperature, it also applies for the heat transfer which is taking place. So, heat transfer which is taking place by the conduction, convection or radiation. So, they also should have the same ratio as in the case of model or in the case of prototype. So, that is what the thermal similarity means. So, we can have the discussion about the similarity criteria by even working with the equations, and that is another way of looking at it. So, suppose we are talking about the Navier-Stokes equation. So, I mean there also you can have the terms, we can go for individual terms, and we can have with the help of the dimensionless numbers we do the analysis. So, the Navier-Stokes equation, which is normally you can you express it as rho dV by dt. So, this is your total derivative term d by dt of V, it will be minus of grad P, and then you will have eta grad square V, and plus you have rho g. So, this is your another term, that is the source term. So, now in this case what we do is we non-dimensionalize these terms. So, using the non-dimensional quantities we are making the V star. So, suppose V star is as V by B, or we take X star as X by L. So, the characteristic length of the tundish. You further non-dimensionalize T star, that is T into V by L. So, it will be T with a certain time we are dividing. Then you have P star, we define as P minus P naught and divided by rho V square. So, this is how P star is defined. You define grad star as L into grad, and then you have so grad star square term will also come, which is here. So, that will be L square grad square. So, that way if you use these non-dimensional terms, so if you substitute these non-dimensional numbers into this equation, you get the further the term, that is dV star upon dt star. So, if you use them, you get minus of grad star P star. Then you are getting a term, that is eta upon L V rho, and then you are getting grad star square and V, and then you have another term as GL upon V square. So, what you see in these cases, you have in this term under the in the parenthesis you have two terms which are coming up, and they are basically, this is the inverse of the Reynolds number, this is eta upon L rho v. So, and then you have, this is the inverse of the Froude number. So, these terms are coming, and basically these are the important forces which are governing inside the tundish. So, this is coming because of these inertial gravitational and viscous forces. So, there has to be a constant ratio of these forces. Now, if you imply the inertial forces which should be if you talk about the Reynolds similarity. So, that is why you have the Reynolds similarity as well as the Froude similarity which is coming up, and you have to maintain that. So, if you try to see the Reynolds similarity, so in that case you have V L rho upon eta of the model should be V L rho upon eta of the prototype. So, what we see that normally the kinematic viscosity of the molten steel and the water at room temperature, they are somewhat similar. So, they are somewhat equal. So, eta by so this ratio becomes 1. So, in that case what you get is, so your eta by P rho of water at room temperature and that of steel at 1600 degree centigrade. So, they are nearly same. So, what we get out of this similarity principle, that this Vm and this is your Vp, and similarly this is Lm and Lp. So, if you lambda eta by lam rho, that will be cancelled. So, Vm by Vp will be L P upon Lm. So, basically you will have the inverse of the scale factor. So, what you see is Vm will be 1 by lambda of Vp, that is what you get. So, because its ratio will be 1 by lambda, that is your geometric scale factor. So, lambda is the length scale factor. So, the Reynolds similarity gives you this condition. Now, if you go to the Froude similarity, if you further use the Froude similarity. So, using the Froude similarity, what you see, so you can further do the same calculation. So, you have V square upon GL of the model should be equal to V square upon GL of the prototype. Now, from here as G will be same. So, what you see is that V square of V of model by V of the prototype. So, basically you will have a squared term. So, you will have Vm will be Vp into under root of lambda, because it is Lm upon Lp, it is going on this side. So, Lm upon Lp is lambda. So, Vm will be lambda under root lambda times Lp. So, that is you can see that this is Vm and this G term will be cancelling. Now, what you see that you are getting Vm and equal to Vp under root lambda in this case using the Froude similarity, and using the Reynolds similarity you are getting Vm as 1 by lambda Vp. So, you are getting the different values different proportionality factor in these two cases. Now, if you try to have the that try to ensure that both these conditions, similarity conditions are satisfied, that is only possible when you have lambda that is equal to 1. So, that is when you are making the model of the same scale as that of the prototype, then only these two can be satisfied. So, both these conditions can be only met when you have lambda equal to 1. So, that is your scale factor is 1 itself. So, you are having the model as well as the prototype of the same dimension. So, that is of that cannot be said to be a feasible solution. So, now if you look at this Reynolds similarity, so in that case what you see is that the velocity of the model. So, when you are making a scale down model, in that case lambda value is less than 1. So, in that case the 1 by lambda value will be more than 1. So, in that case your velocity in the model has to be more than that is what it is there in the case of prototype. Whereas, if you take the Froude similarity criteria, here the velocity in the model will be less than the velocity in the prototype. So, it is because it is under root term. So, so normally what we use, so basically that is this value will be less than 1. So, so that way model will this value will be lesser. So, normally when we do the physical modeling, we do this by assuming the Froude similarity criteria. So, so that is the normal practice in the case of physical modeling. Apart from this, as we had discussed, that apart from that this geometric similarity, dynamic similarity or kinematic similarity and thermal similarity, many a times we also come across the term known as the chemical similarity. So, when we talk about because many a times these there are many type of chemical reactions which are taking place. So, you will have to deal with the concentration profiles in the full scale system. So, you will have the discussion about the chemical similarity, in which you will be talking about the concentration differences at the corresponding locations in the model and in the tundish. So, if you have the concentration difference between two positions in the model certain value and similarly the same value in the tundish, I mean in the actual case in the prototype. So, they should bear the same value. So, this may be because of the diffusion, you will have the mass transfer taking place, you will have the mass transfer by convection, maybe by diffusion, or maybe many a times you have the generation of the species or dissipation there through the chemical reaction. So, these quantities also need to be bearing a certain ratio, and that is taken into considerations by taking this chemical similarity condition. So, in this case what we tell is that you have the suppose you are talking about the diffusion. So, and diffusion in the model, and if you take the ratio of diffusion that is in prototype. So, that ratio should be suppose you are talking about the using the convection in the model and ratio by for convection in the prototype. So, similarly if you are talking about the radiation quantity. So, all these values they should be having a constant value, that ratio should be same. So, this means there is a chemical similarity. So, these are the different kinds of similarity principles which are need to be addressed into and which must be satisfied when we are talking about the physical modeling. And altogether, when we talk about the static or dynamic similarity, they are also known as the mechanical similarity. So, many a times we talk about the mechanical similarity as a whole. So, these different kind of similarities are there which needs to be seen, and many a times this chemical similarity is very difficult to be achieved because of their strong dependence on the temperature. So, in many cases it will not be feasible to have these similarities. However, we must know that what the chemical similarity means, because when we do the suppose we are talking about the chemical similarities in two systems. Now, in those cases the temperature being higher, many things change by orders of magnitude quite high because of the temperature. So, that may not have the similar ratios, but then many parameters may be checked, like the diffusion of certain things which is not temperature dependent, or when we do the cold modeling studies, in those cases the chemical similarity holds certain meaning. So, we will talk about other aspects of the physical modeling, like use of dimensional numbers or so, in our coming lectures. Thank you very much.